Hi, and you're all very welcome to Spectral Augmentations for Graph Contrastive Learning. I am Amur Ghose, and these are my co-authors, and we are representing these institutions, and this is obviously 2023, so let's begin. So first, I want to talk a little bit about contrastive learning by itself, which is trying to learn augmentations, which can be thought of as just operations, and we can term them as A1, A2, and so on, and they work on data instances Xi, so that when you operate A1 on Xi or A2 on Xi, you basically get the same object Xi back. For example, if you have an image and you crop it and you keep the same object in focus, then the label of the image probably didn't change because you kept the same object in focus, which is probably the label. Or if you have a sentence and you change a minor word, then important semantics about the sentence probably didn't change, right? So the augmentations are kind of changing the object itself, but not the label it usually has. So for example, if I'm going to skip the slide a little bit. One of the examples is crop for images, right? So if you have an image like this label will be probably what? Child, a female child, I mean. But if you crop it and you get this, sure, you change the image, the background is gone now, but did the label change? Probably not, because that's what the label was likely, right? So cropping is a valid augmentation for a set of images if the label is the object in focus and the cropping keeps the same object in focus. Now, we usually write this in terms of inner products. And if we have A1 and A2 from the first step, we call this a contrastive pair. Sometimes we don't even get an A2. We get Xi itself, and we just have A1 Xi. So the one valid augmentation you always have is just keep it unchanged. Then if you have some neural model, for example, for images, suppose it's a ResNet or something, and the representation would be some hidden there, you would be maximizing a term of this form where R is the hidden representation of the augmented instance. Now, this is not the exact loss because there will be some other terms arising from the other pairs. Like if you have A1Xi, A2Xi, that's a valid contrastive pair. But we also have things like A1Xi, A2XJ, and those are going to go into a normalization term in the denominator. I don't show that, but this is a simplified form. Now, having talked about contrastive learning, I want to talk about the formulation for graphs. So generally, we don't consider the graph as whole, right? The graph could be really large. It could be a social network graph. We are talking about hundreds of millions of nodes, maybe sometimes. But instead, we want to talk about an ego network, which is nodes within distance k of some fixed nodes. So for example, here, I've highlighted this node n in this big graph. And this is the ego network of n, where the distance k is 1, right? This part in blue, that's the ego network, just the neighbors of node n here. And we can just work with the ego network sometimes. So if you have a node classification problem and the label is whatever n has, then you can turn it into a graph classification problem by replacing the node n with the ego network of n, right? And you just inherit the label of whatever n has to the ego network around n. So this allows us to turn node classification into graph classification, which is often quite useful if you have augmentations that work on graphs, per se. So a very strong augmentation is just the random walk. And the random walk, well, we probably know what it is, but to refresh your memory, if we have at time t, our random walk at node I, and starting from node n, of course, we will be moving to a neighbor of I with probability 1 minus p, and we can move to each of the neighbors with equal probability. So that's going to be di, degree of I. Or we can move back to n with probability p. So here we could also move back to n from 10, by the way, if the ego network goes up to 10. So we don't need to be next to n to return to n. So this return probability is often quite high. Like the core work in this domain is graph contrastive coding, but the return probability p in this, as far as I remember, is 0.8, which is quite high. So generally, what happens in random walk is that it subsets a group of the nodes, which is quite close to n, and kind of gives you a view around n. And these different views form your contrastive pairs. But our framework is going to focus a little bit differently. And our flowchart is something as follows. You can see we still have the random walk here, and we have augmentation filtering. I'm going to talk about the next. Graph cropping, alignment, and reordering. I see there's a typo here. Anyway, the figure is as per the paper, sadly. So reordering, alignment, cropping, filtering. And what are these? Let's talk about that. Cropping. Right. So for image cropping, we just established that image cropping is quite powerful, right? And it's worked for things like SimCLR, CPC. These are very prominent papers in the field of image contrastive learning. We want to generalize it for the class of all graphs, but how do you even crop a graph? Well, this is a line graph, and this is a grid graph. And well, a grid is something like if you have a line and you make a multiplication in the graph domain with another line, right? And I have taken the first two non-zero eigenvalues of the Laplacian, taken their eigenvectors and plotted them on these grids. And you can see that they have recovered the axes, right? This is the y-axis, the x-axis. The colors represent the values. So maybe what's going on is like this. We have graphs as the domain G, and the images are as I. And you can kind of write an image as a grid graph, right? So we can perhaps say that I is a subset of G. And we want to find a good augmentation on G. And we have a good idea of what augmentations work well on I, right? So the idea is something like function extension, where you have a function that works well in a domain and you want to extend it to the unbounded domain. And does that work here? We have the function of cropping, which works well on images. Can we extend it to the class of all graphs, knowing that cropping works really well? And we know that if we take cropping and make it into the first two eigenvectors being considered, it will generalize to the grid graph at least. So maybe that's our claim. The first two eigenvectors corresponding to the non-zero eigenvalues, not the zero eigenvalue of the Laplacian. This should be understood to be of the Laplacian. If we subset along the ranges and take the intersection, that's an augmented view. So what does it mean to subset along ranges and take the intersection? Well, a range in the y-axis is like from here to here, and the range in the x-axis would be from here to here. So basically a rectangle in the grid graph, i.e. a crop, right? So that's an augmented view. Now, we also introduced reordering. This is based on two key ideas. If you have the adjacency matrix A, and if you replace it with a power sum like this, it's also useful. The entries in the power sum represent the number of paths from I to J. And we always compute the eigendecomposition of A. Okay, technically we compute the eigendecomposition of the Laplacian, but that's often done just by doing the normalized adjacency matrices eigendecomposition. So you can think of us having A's eigenvalues and eigenvectors. But if you have A's eigenvalues and eigenvectors, then you know this is very trivial to get because the eigenvalues kind of come out in a power sum. We're not going to show the derivation here, but this becomes easy to deal with if we're doing this anyway. So we can swap our derived embeddings to be from either A or this. And you can actually show that there's a difference between K being even and odd, and you can check that in the paper. But this kind of formulation is very cheap in terms of runtime if you are doing this. And it's a free way to augment your training pairs. Next, we want to talk about alignment. So in alignment, if we have the global graph and if we have the R ego networks and we have the random walk, right? So that's going to give us, let's say, two views like this. We have the shaded ellipses. And we want to take out the same node in both ellipses, i.e. views. And this node, right, the one I marked with a black cross, and this purple node here, if you take their embedding based on the Laplacian embeddings, you'll find that they're not equal, because even though they are part of the same global graph, the structural embeddings are reflected affecting the structural role they play in the extracted subgraphs. So the structural embeddings are not going to be equal, but we can align them using a global embedding matrix that we can compute over the global graph once for free, which we can get using things like node-to-vec, line, or any other valid node embedding method. We are not going to say that it's restricted to node-to-vec, but you can use this as an auxiliary matrix to align these two for very cheap computing cost. And that provides another way to correct our augmented pair. And the way we do the alignment is Wasserstein-Procrustes, which is the idea of Wasserstein-Procrustes can be summed up as, if this is your graph and this is another graph, I mean, you can see they're structurally equivalent. You want to kind of line them up. Then you can do it with a permutation matrix and with an orthogonal rotation matrix. And with all of this, the idea is that if this is the overall graph and X, WY, and ST are one part of the graph and PQR, ST are another part of the graph, the embeddings of S and T would be brought closer together than if they were completely ignored and just set out in the way we usually do them, which is directly by a Laplacian. And we do that with a global embedding. And you might think the global embedding might be very expensive to compute, but compared to the training cost, it's actually quite low because of the advances in scalability that we've made in the field of global embeddings. Now, similarity controlling is another thing that we can do with the global embedding. Because, as I said, the global node embedding is very cheap to get. And we are having it anyway. So if we have two candidate subgraphs as our views, we can pool their global node embeddings and to get the overall embedding of the subgraphs. Now, if the overall embeddings are similar in terms of the inner product, then that means the two views are very similar. That could be good or bad, right? Or if they're very different, i.e. the inner products normalized are far from one, then they're very different from each other. Again, you could either accept that or you could accept the similar one. And we find that similar filtering is actually a lot better. Again, results are in the paper. So these are our results, right? These are a lot of relevant benchmarks over the recent years. And this is like a rank plot. The triangle represents the mean rank. The box is the range of variation. And you can see that our rank tends to be among the better ranks. But depending on your data set, there could, of course, be a stronger method. But what we would like to point out is that it's not consistent what the other stronger method is. Whereas with this, you get a good result all the time. So some representative results on graph classification on various data sets. And you can see that our results are quite strong. And we have results across MOCO and E2E, which are two different ways of doing the contrastive learning. So that's also checked for. And even though I only put the graph classification results here, you also have the node classification results elsewhere. So yeah, we have tested across a broad variety of cases and it has performed well. Thank you.